Okay, so this is the last lecture of Professor Upendra Kulkarni. Please start.
Okay, so remember the task that is left for us, at least in terms of the main theorem that we wanted to prove, which was that a quiver is of finite type. That is, it has only finitely many indecomposable representations, if and only if it is of type ADE. Now the ADE we showed that it is equivalent to the quadratic form associated to the quiver being positive definite, and we really did show that one direction of the theorem, that is, if the quiver is of type ADE, or more to the point, if the quadratic form is positive definite, then that allows me to have this beautiful finite set of vectors called roots. Each one of them is positive or negative, and we showed that the indecomposable ones are really in one-to-one correspondence with the positive roots, and we in fact showed how to construct it. Right? So there was that beautiful picture which you should keep in mind, because we will revisit this picture in in slightly different formulations today too. So what is left to be done? We want to show the other way around. That is, if the form is not positive definite, then the number of indecomposables is infinite. So somehow I have to produce these infinitely many indecomposables, one way or another. So one indirect way of doing that is to use a little bit of algebraic geometry, which we will try to do at the end today. But let's go and do representation theory and really see how to produce infinitely many indecomposables. So one small part, yesterday we had a list of 7 equivalent things for an indecomposable representation. So I just want to remember one part of it, which is that if the reflection functor fi plus is defined at some point and you apply it to an indecomposable V, then not only do you stay indecomposable, but if I apply fi minus, I come back to the same one. So that is the situation, with exactly one exception, and that happens when V is SI, and in which case the functor just kills it. So you either come back by means of fi minus or you die. All right. So this gadget, provided I could find a source, provided I could find a sink or source for fi minus, this gadget is just completely general for any quiver whatsoever. But to guarantee that I will be able to apply this, for every vertex once, I should have, it's necessary and sufficient, we saw yesterday, that if Q is an acyclic quiver. So now we are going to stick to acyclic quiver. And so I have an admissible ordering of the vertices. Remember that one way to do this is to ensure that if there is an edge from a I to J, then the label I should be less than the label J. That ensures that I will be able to construct such a sequence of functors, and it is valid. So Fn plus, Fn minus 1 plus, it's applied in that order, though of course when I write it, it is F1, F2, and so on. So now I give this a name. I call it a Coxeter functor. Yeah, and because it is being applied at every vertex, every edge gets reversed twice. So after doing this entire sequence, I'm come back to the same thing. All right. So remember, there are no loops also. That means every arrow is going to participate in exactly 2 vertices. All right. And likewise, so we had this picture, that you start with a representation. Let's see a version of this. We will come to. Okay. So ignore this pi, whatever. So I start with any representation V, and I'm applying Fn plus, etc. And I go all the way up until the end. That means that I will be able to apply the minuses in the opposite order. Okay. So this other Coxeter functor C minus also makes sense, where I have the same functors with minus versions and chained in the opposite way. So first F1 minus happens, and then so on and so forth. And then I start taking powers of these. So C cube is C plus, C plus, C plus, and C to the minus 2 is C minus, and so on and so forth. Okay. So it is a fact that these functors are actually independent of the admissible ordering. So if I choose a different admissible ordering, then I'm going to get the exact same Coxeter functor. So they're intrinsic in some way. And in the next week's lecture, you will see another incarnation, another way of getting these functors. All right. So just to state the very final thing, what we are going to say is that to get these infinite Riemannian decomposables, I'm going to say that it is enough to do that for Euclidean ones. For Euclidean ones, for the cycle, I will do it using a Jordan block, because there are infinitely many Jordan blocks possible. And for acyclic ones, the infinitely many indecomposables will precisely be the C minus S applied repeatedly to the PIs that I defined yesterday. Okay, so let's remember what the definition of PI was. So for that, let me go to yesterday's notes. Yes, yeah. Okay, so general things. So remember that when I have a quiver Q, I get to associate a category to it where the objects are just same dots and the morphisms are paths, where I include the empty morphism at, the empty path at each vertex, which acts as the identity there, because the composition is just by concatenation. All right. So given any category, given any quiver, I get a category where the morphisms are now just sets. And given any category, I can k-linearize that category by taking morphisms between any two objects as a basis of a vector space. And that will give me a k-linear category, which you can think of as a ring with several objects. If you have not heard that term, don't bother, it doesn't matter. The point though is that in this category, I have the Hom functor. Okay. So I just take, I fix an object I, and I just take the vector space with basis all paths from I to any vertex j. That is the vector space associated to the vertex j. All right. And then we saw that the key Yoneda lemma gives us a bunch of things. So the morphisms from any pi to v is just any representation v is just the vector space of v sitting at I. This tells me that all the PIs are pairwise non-isomorphic because each one can be detected by means of this VI. So in particular, I can use SI to detect the vertex I at which PI is sitting. And moreover, the fact that this PI is a projective object in the category, that means that the Hom PI dash that functor is an exact functor. Okay. So the only thing to remember at the moment is how the definition of PI is. PI sitting at any vertex J is just the set of all paths from I to J taken as a basis of a vector space. Okay. So let's go back and prove another key description of this space PI, of this representation PI. So my claim is that the dimension of PI is precisely going to be obtained by taking the basis vector at I and then applying the reflections sigma I plus 1 up to sigma n in that order. Okay. Once we have this key thing, which is where some combinatorial work is required. After that, the second result will follow by using the magic diagram from yesterday. Okay, so let's see what's going on over here. So I take this alpha I and I apply sigma I plus 1 to that. So I know the formula. The vector stays unchanged and I subtract from it the bilinear form evaluated on I plus 1 along with the vector to which I'm applying the sigma I. And then I put alpha I plus 1 because that is the reflection that I'm applying. Okay. All right. Nice and good. Okay. So what is the bilinear form evaluated on? In fact, these are two basis vectors. So you remember what the matrix of the form is? Here, the arrows do not matter at all. This depends only on the underlying graph. Okay. However, okay. And then what do I have? This alpha I plus 1 is just minus of the number of edges between I and I plus 1. Okay. So this is what I have. Alpha I This became plus because the value of the bilinear form itself is minus. So alpha I plus the number of edges from I to I plus 1 times alpha I plus 1. However, now I slipped something in, you see. I said that the bilinear form does not depend on the orientation, but here I'm saying it's the number of edges from I to I plus 1. Why can I say that? Because now suddenly from undirected, I have gone to directed. I'm looking at the quiver. The answer is very simple, because all the edges that connect vertices I to I should really say arrows over here. Let me do that. And anyone? The reason is very simple, because I have an acyclic quiver. So, okay. So very basically, if there is an arrow from I to I plus 1, there cannot be an arrow from I plus 1 to I. But you see, there cannot be an arrow from I plus 1 to I anyway, because of what? I choose an admissible ordering. That means that whenever there is an arrow from vertex V to vertex W, the label of V is always less than the label of W. Yes. So every time I have arrows between any two vertices, they can go only in one direction. And I know exactly in which direction they can go. That means that this is really the number of arrows from I to I plus 1. But look now, what have I done? I just replaced the word arrows by number of paths. So what I'm saying is that, yes, all the arrows from I to I plus 1, they will of course be paths from I to I plus 1. But I'm saying that there are no other paths. Why is that? Just think for a moment. Yeah, and then you see again it's the acyclicity and my nice ordering. Because if I want to go from I to I plus 1, if I want to go through any other vertex, first of all, I cannot go back to I or to I plus 1. There are no loops, correct? However, if I go from I to any other vertex J, then J has to be bigger than I. Otherwise, there is no edge. I cannot go down. And if I go to something bigger than I, which is not I plus 1, then I cannot come back to I plus 1. So it is because of this observation that this really is the number of paths from I to I plus 1. And now I just continue. I show that, so if I apply sigma, sorry, this is wrong. This is wrong. So what I'm going to do is now I'm going to apply sigma I plus 2, not to alpha I, but look at the picture that I have. I'm just going to apply a chain. So let me just use this. I'm going to say first apply sigma I plus 1, sigma I plus 1, I plus 2, all the way up to sigma I plus L. I claim that when I do this, I get the exact same result, which is for every vertex, sorry, this also, sorry, I plus J. Okay, so notice what is written over here. For every vertex from I up to I plus L, the coefficient of the corresponding vector is the number of paths from I to I plus J. So how does this work? So see, this is just straight induction. All right. So let us suppose that I have gone all the way up to I plus L minus 1, and I'm just including I plus L. Okay. So let us say that this works out until the last but one step. So that means before applying this, I have the exact same thing over here, except the very last term, alpha I plus L. So what do I have? There are all the, let's draw a little picture over here. There are all these vertices I plus 1, all the way up to I plus L minus 1, doing something, okay, connected in some fashion. And there is IL. What happens when I apply sigma I plus L to that entire expression. Remember that entire expression is now summation j going from 0 to L minus 1 of the same thing. This guy over here. Let me see if I can just state. Okay, so this is what I have by induction. And now I'm going to apply the sigma I plus L to it. Well, what happens? IL. What happens when I apply the sigma I plus L? The sigma I plus L applies to every single one of these things. And when it applies to I plus J, what is the extra thing that I get? Of course, all of these terms stay, and the analog of this thing comes, right? Except instead of I plus I plus 1, it is going to be I plus n, and these are going to be I plus j. So whenever I have some vertex I plus j over here, the thing that gets added is every such edge. The number of such edges gets added to whatever was the coefficient of alpha I plus j. To that I add the number of edges from I plus j to I plus l. But that's precisely saying I'm taking the paths from I to I plus L that pass through I plus J and connect by one extra edge. That's exactly how all the paths from I to I plus L are made, you see. Every path from I to I plus L can go only through these vertices for the same compatible, for the same nice or, for the same admissible ordering reason that I have. Okay. So this is really the only place where some kind of combinatorial nice work happens. All right. So I claim that now I have proved this result by induction, the first one. Because how do I reach in the end? Pi simply means I have to, Pi means I have to, I'm going all the way up from to sigma 1 up to sigma n. And you see, this is going to tell me all the paths from I to every vertex up to n. But those are all the paths from I. You see, there cannot be any paths from I to any vertex that is smaller than I. Okay, so this is kind of a key thing, and the rest of it is going to be, we are going to use yesterday's picture once again. So if there are any questions, please ask me now. And if something is unclear, you can sort it out later. The issue, the thing is that everything is turning based on having this admissible ordering, and just the formula for reflection that I have. And this bilinear form is really just the number of edges minus the number of edges between the two vertices. That's all that is making everything work. Okay. All right. So let's move on, and let's now try to do the second part. So just the dimension vector allows me to exactly write down what this Pi is in terms of my reflection functors, starting with a simple model. Okay, so let's see what's going on. One thing to note is that, again, remember the proof. What did I do? I started with alpha I, and I applied all of these reflections in order to finally come to the dimension vector of Pi. Notice also that by means of this lemma, everything in between that I got, every one of these things, just look at the formula over here. Every one of these things is a positive vector. And we know exactly how positive, and we know that when vectors stay positive after applying sigma i's, nice things happen. So let's examine those nice things. Okay. So this is an analog of yesterday's magic picture once again. Don't look at the top line. We don't have representations yet. Let's just look at the bottom line. Okay. So what did I do? The way I started was I actually started at the right end. And all of these arrows, the way the proof worked over here is I'm going from right to left. But you see, sigma is a reflection, so it's bidirectional. So alpha I goes by sigma I plus 1 over here. That means I just come back. All right. So I go all the way back over here. These are all the vectors that I met along the way for which I had proved formulas. And I land up over here, which is the dimension vector of Pi, right? So this part I have. But you see all the vectors down here, they're positive vectors. Okay. And what that means is that if I take this Pi and apply the reflection functors pluses now, Fn plus, Fn minus 1 plus, and so on and so forth, then I'm going to end up to whatever was the representation over here. But remember, the dimension vector over here is alpha I. That means what is setting up here is Si. So the upshot is that starting with Pi and applying Fn plus 1 first, then Fn minus 1, all the way up to Fi plus 1 plus. Because remember, that is the last thing that is what? That is the going in. Sorry, I made a mistake over here. No. This is all right. This is perfectly all right. Yeah. This is perfectly all right. Okay, so this means that this Si is obtained from Pi by applying the reflection functors in the correct order, n minus 1 and so on, but I stop at I plus 1. Okay, but what does this mean? Starting from Pi, by means of applying this sequence, I got to Si. That means that if I start with Si and apply the minus functors in the opposite order, I will get Pi. That's exactly what this is saying. Remember, for Pi, I first applied Fn, and then finally I applied Fi plus 1. So over here, I apply the minus version of Fi plus 1 first, and then all the way up to F. So this is my other construction, nice construction of the indecomposable Pi. So let's remember this, right? So I get indecomposables also by means of simple, by means of these simple modules. See, what is happening here is, the overall procedure is similar, but it's happening in a very different way, right? Yesterday I used, so go back and see, compare between them. All right. So what are the consequences for an arbitrary indecomposable? Right. So I start with an arbitrary indecomposable representation. I claim that if it is one of these projectives Pi, then if I supply C plus to it, then I just die. Okay. But look, it's all in the picture. What does applying C plus mean? Remember, C plus is just F1 plus F2 plus up to Fn plus. That means I first apply Fn plus and then work my way backwards all the way up to F1 plus. So let's see what happens. This picture shows me that if I take Pi, apply Fn plus all the way up to some positive Fi, then I'm landing in Si. Well, what is the next thing to apply? Well, it tells me C plus means either I have to go all the way up to F1. No? So I'm over here. That means I just have to apply now. The next one to apply is Fi plus. Well, what happens? I die. And once you are 0, you're forever 0. Right? So this is the thing. But the interesting thing is that the converse is also true, which is that if C plus of V is not 0, then I cannot be Pi. Oh, sorry, that came out wrong. What I mean to say is that if V is Pi, then C plus of V is 0. But if V is not Pi, then C plus of V is actually non-zero. Why is that? Because what we will say is that if Pi is not one of these special forms, if Pi is not one of these special forms, which I have not written over here, maybe let's just, okay, we can remember. If Pi is not one of these special types of vectors, then if I apply C plus to it, I will not die, because by means of C minus, I'm coming back. So how could this C plus V be 0? All right. So let's try to prove this. I'm going to claim that if V is not one of these principal projectives, indecomposable projectives, then C minus of C plus V is V. And remember, it's an indecomposable V. So V is non-zero to begin with. All right. So if C minus C plus V is not V, then what can it be? Well, it has to be 0. Why? Because look what's happening. This is what we said right in the beginning. If I have an indecomposable, after all, this C plus and C minus, whatever, it's just a chain of reflection functors, right? So if I apply a reflection functor at any time, I either stay indecomposable or I become 0. All right. So if not, I have to become 0. But then you see, if C minus of C plus is 0, then C plus V itself has to be 0. Just think about it. Because if C plus V is non-zero, if this is non-zero, then just look at what's happening in the picture. I'm starting with some V, and this Fn plus all the way up to F1 plus is keeping everything non-zero. But if that is the case, I know that at every stage, if the result is non-zero, then when I work backwards, I'm just going to recreate what I started. So what this says is that C plus V itself has to be 0. But what does it mean that C plus V is 0? It means that if I start applying Fn plus, I just do the same thing once again. Whatever module I have, if I apply Fn plus, then Fn minus 1 plus, and all the way up to F1 plus, at some point I become 0, right? That means at some stage I was non-zero, and applying the next Fi plus gives me 0. That means I must be in such a situation at some point. That means whenever I die, the previous one must be Si. I just work backwards and get a formula that whatever I started with must be precisely of this type. Okay. So all of this is just the magic of these reflection functors. So this should be seen as the analogy of what happened yesterday with individual reflection functor. That an individual reflection functor, I apply to something, then that something dies or stays indecomposable and I can come back. But what is the special one that dies? The special one that dies is the simple one. Today what we are saying is that something is exactly like that true. It's true for the principal projective, and that is this for every principal projective, which is this criterion. If C plus kills it, it has to be a principal projective. Otherwise, you will just come back by means of C minus. Okay. All right. So what this tells me is that if I apply this Coxeter functor, the positive Coxeter functor to an indecomposable projective, I'm going to die. So the interesting thing to do is to apply the negative Coxeter functor and see what I get. So this is what I'm going to say, that if I apply a negative power of a Coxeter functor, that is, if I apply C minus a certain number of times to a principal projective, if I get in every non-zero module that I get of this type is called a preprojective. But again, remember that just means that if I get a non-zero module by means of applying C minus sometimes, then every application of C plus is just going to get me back, right? So what this says is that V is preprojective if and only if, of course, it has to be indecomposable to begin with, right? If some power of the Coxeter functor kills it. Just think about this for a moment. If I am preprojective, then of course the first power, that is C itself, kills it. If I am C minus applied to some Pi, then I apply C to come back to P, and then the next C will kill it, right? So let us say if I have taken some principal projective and if I applied C minus 10 times to it, then the resulting thing will be killed by 11 applications of C++. So that is what a preprojective is. All right. So what is this? Now, okay. So this claim is going to be useful for us. Yeah. So what does this say? This is a detection criterion for an indecomposable projective. For a preprojective in terms of its dimension. So what it says is that if I'm given an indecomposable V, then it is of the type C to the minus RPI, if and only if the dimension of it matches the dimension. Now we are playing the same game again and again and again. So I'm not going to say anything about this. In one direction, it is okay, right? Because if V is of this type, then of course the dimension of it, I know exactly how to apply the formula. Right? This PI, its dimension is that. And okay, so there is one small thing to say over here. This is capital C. And this is small c if you want. The small c is the Coxeter element, right? The sigmas, sigma 1 up to sigma n chain together. Okay, so the forward direction is already done. And for the backward direction, what do I have? Suppose I have an indecomposable V whose dimension vector is this. Well, just use the same diagram once again. Take this V, take its dimension vector, walk forward in order to go to alpha I on the lower line on the dimension, and therefore say that if I apply the respective reflection functors above, then I must recover the original representation. That's it. We played this game many times. Okay. So an upshot of this is that if I'm given two indecomposable, if I'm given two preprojectives, right? By the way, I should say that all of these preprojectives, etc., everything is indecomposable. As long as it is non-zero, it's indecomposable because I'm starting with. So if you want, here's another proof that PI is indecomposable because looking at this formula, I started with an indecomposable and applied reflection functors to it, and it did not die, so it must be indecomposable. And likewise, the preprojectives are also indecomposable as long as I'm getting a non-zero model. So what is this thing saying? It says that if I start with two different PIs, sorry, this should be PJ. So if I start with two different vertices and take the corresponding projectives Pi, and if I apply some negative power of the Coxeter functor to each one, and suppose I get indecomposable, suppose I get non-zero modules, and suppose they're isomorphic, then I'm claiming that it just cannot happen. You must have started with the same I and J, and this R and S must also be the same. Well, why is this the case? Let's see. Let's suppose that whatever. Let's say that C to the minus 3 of Pi is equal to C to the minus 4 of Pj. And both are non-zero. Well, but this is not possible. Can you tell me why? What happens? So let's try. So what we should do is we should apply C plus to both sides. All right. On the left hand side, if I apply C plus 3 times, I come to Pi, right? I cannot die, remember, because I started with a non-zero thing, and after applying C minus 3 times, I've stayed non-zero. So I could not have died. That means I get to come back. So C cube applied to the left hand side gives me Pi. What happens if I apply one more C?
The left hand side will become 0, but the right hand side
will die. Whereas the right hand side will become P sub J, which is non-zero. And whatever, it could be some C to some different power. It doesn't matter, right? So what this says is that the two powers have to be the same. But if the two powers are the same, then I cancel that same power on both sides by applying C plus that number of times, and I will get Pi is isomorphic to Pj. But we saw that by Yoneda, this cannot happen unless I is equal to j. So this is the all right. So what I want to say now is that if we have time, maybe we will see some of this. But there is an entirely parallel development for injective modules. Okay. So for a basis for projective module, the concrete incarnation was what? I took all the paths from I to any given vertex. So here I should consider all the paths to a given vertex. That's what is going to be I. Injective modules in general are harder than projective modules, but in this particular case, there is a duality, simple duality, because of which things work nicely. And there is an exactly the same parallel story. So I'm going to get an analog of the dimension in terms of I'm going to get an analog in terms of dimensions of such things. So I will show what, and so I will get a formula for the injective in terms of the simple. But of course, the functors that will apply over here will be the pluses, appropriate appropriate pluses, chain of pluses. And what will I have over here? If V is an injective, then C minus applied to that is 0, and conversely. Okay, so remember that, and conversely. So, and likewise, if it is not an injective, then I, by means of applying first C minus and then C plus, I will come back. Okay. Likewise, I'm going to define the notion of pre-injectives, where I start with an injective and I apply a positive power of this Coxeter function. Okay. So I have written some of these here. V is an injective if and only if scaled by C minus. Pre-injectives are positive power applied to V, provided such a thing gives me non-zero. And just like over here, I have a criterion that pre-projective if and only if some positive power of C kills it, pre-injective if and only if some negative power of C. All right, so this is a sort of quick development of the very basic things about injectives, projectives, and how I can generate new things out of them. So in the tutorial, I'm going to ask you to take our usual LinkedIn type quivers, AN and D4, the examples that we've been working out, and ask you, well, what are the pre-projectives, what are the pre-injectives? Well, first of all, what are the projectives and injectives, and then what happens if I start generating other things? Okay, so there is a lot more to say about these, but we do not have the time. Not to mention the lecturer's competence, which is also limited in this. All right, so let's go back to our task. Our task was to show that if a quiver is of finite type, then it has to be of type ADE, and the quadratic form has to be positive definite. So we said that for this, it is enough to, for that, if there is a quiver of any other type, I need to show that the number of indecomposables for such a thing for any other types is infinite. Now I claim that it is enough to do it for Euclidean. And for this, I do a simple trick, just like the trick that we did in the proof of the trichotomy theorem for classifying quivers according to whether the form is positive definite or positive semi-definite but not definite, and not positive semi-definite. That is, Q of some alpha is negative, and this will happen for a positive vector actually. So okay, so what did we do over there? We simply said that, look, if I am able to do something or the other for a Euclidean quiver, then if I'm given some other arbitrary quiver, I will just find a Euclidean subquiver, provided it is not of type ADE, a Euclidean subquiver, and I will just do whatever I want with this Euclidean quiver, and I just will extend it to the larger one in a very sort of simple fashion. So let's do that in the context of representation. So suppose I show that the number of indecomposables for Euclidean quivers, for any Euclidean quiver is infinite. Then I can do it for any other quiver. So what do? I do something very simple. I'm given some other quiver. I find this Euclidean subquiver. Over there, I put an indecomposable. And then for every other vertex that is not in this Euclidean subquiver, I just put the zero vector space. And for every arrow that is extra, I just put the zero map. Now it's a simple matter of checking that a representation that is constructed in such a fashion will be indecomposable if and only if the original representation of that I put for the Euclidean diagram, or for that matter any diagram, this has nothing to do with Euclidean or what. If I extend a representation from a sub diagram to a bigger diagram by means of just putting zeros on extra stuff, then it will not change decomposability or indecomposability. All right. So the problem has reduced to showing that the number of indecomposables for a Euclidean quiver is infinite. All right. So now I make two cases. For the A tilde graph, there is a cycle, no? So for the cycle, I use this trick. So let's just do a schematic over here. So there is this cycle. And you see the cycle may be directed, not directed, it doesn't matter. So whatever, there is some cycle. I will just put some. So what I will do is I will just take k to the n here, and I will put a Jordan block. You can say, well, what if the field is not infinite? Well, it doesn't matter. You just put a nilpotent Jordan block. Doesn't matter. Okay. And then what I do is for all other arrows, I just put equalities. So you see the directions don't really matter. So I just put kn everywhere else. So effectively what I have done, you see, is that I have effectively shrunk this to a one vertex quiver where there is a map back to itself. And now it's a matter of checking that this is an indecomposable. I mean, this is your usual linear algebra classification of modules over a PID. Okay, and the reason why I get infinite is because I can just vary this n. Even if my field is finite, I can just take this n to be, infinitely many values. So okay, so this is one thing. All right, so I am done for the cycle case. So if I am not in the cycle case, then I just have to deal with d tilde and e tilde. So you can say, well, I can try to do case by case, but this is kind of the beauty of this whole root system, Dinkin diagrams and root systems. It gives you a conceptual way of dealing with all this combinatorics. So what do I do for type D and E? So here the claim is that I take so this is so I take all the preprojectives. That means I take every vertex, and I take all the negative powers of the Coxeter functor. So C minus applied a certain number of it. And remember the theorem that we proved, that all of these, it's right here, that all of these, if I take distinct I and J and distinct R and S, then no two of them are isomorphic. So you can say, great, I got as many infinite families as the number of vertices. For every vertex I get an infinite family just by taking powers 1, 2, 0, 1, 2, 3, 4, and so on of the negative Coxeter functor. However, there is one problem here, which actually Amit pointed out yesterday until I had not realized this. We have to know that these modules are non-zero. So how? Because otherwise, this doesn't work. I have to know that these modules are non-zero. So how do I know that these modules are non-zero? Well, so the thing is that if this is 0, then notice what is happening. Just look at this PI. this pi, some negative power of the Coxeter functor applied to this is dying. But that precisely tells me that some negative power of the Coxeter functor dies on an indecomposable representation. That means that it is a pre-injective. So somehow I have to, so this is where I have to do a job, where I have to say that, look, this pi is not a pre-injective. It's not a pre-injective representation. And at this point, I have to chicken out because we just don't have enough time. But I will make some noises that. So this takes some job. And the way this work happens is that you go back to the root system of this Euclidean diagram. And remember that in this diagram, I have this special vector D. So I use this special vector D. Remember, this vector is a sincere vector and it is in all slots, it is positive. Okay. So I use this vector D. And what I do is the following. So let's go and let's go and look at yesterday's lecture, because I want to give you at least some idea of what's going on. So all this, so remember all this magic picture that we had, what allowed us to get started? What allowed us to get started is that we started with an arbitrary dimension vector of some indecomposable, and we said that, look, the way I cannot even go to this line unless I go forward and I get a non-positive vector. It was only that which allowed me to say that, oh, look, this is a non-positive vector. Therefore, and remember, this was a I'm confusing two different proofs. Let's look at the last one. If I started with a root, correct? If I start with a root, how do I know that the root will eventually become negative? So when does it become? It will eventually become a non-positive vector. The only way it can become a non-positive vector is if the previous step is alpha n. Okay. So just to get started, I needed to have this result, which I proved earlier, that this was the last bit of work that we did in this. Yeah, Coxeter element. We had this key fact that the Coxeter element takes any positive vector and some power of it goes to, some power of it will have negative entries. Let's try to examine where if I can try to do such a thing for the Euclidean case. And the answer is no. Okay. So let us see how this proof went. First of all, I said that some power of this element C has to be identical. For that, I needed that the group was finite. The finiteness of the group came from it being a, the finiteness came from the form being positive definite, because you know, it was characterized by how it permitted a finite number of elements, right? And those finite number of elements were an orthonormal basis. I mean, I could take an orthonormal basis. Anyway, so in the Euclidean case, the form is not positive definite. So this argument breaks down. However, we say that, look, I can still do something like this. The extent to which this fails is really only one radical vector. There is only that one special vector D, and everything in the radical is really just integer multiples of this. So somehow I still try to play with powers of this Coxeter element, and I try to characterize when a module is projective and injective, and more generally when a module is pre-projective and pre-injective, by means of calculating a certain bilinear form with this special vector. Right. So I'm really not going to say anything more, but let's maybe do one more thing. Special vector D. So recall what property D did what property did this vector D have? If I took the bilinear form of D with any x, what did that give me? Come on, this should be. So the quadratic form on D was 0, and in fact we said that not only is the quadratic form 0, but D is in the radical. That means D along with any vector is 0. All right. So now what we show is that there is another form which is not symmetric, and so this form is not going to be symmetric. Euler form. So what happens is that this is a general result. All right. I should really not say that this is equal to 0. This is a general result. The bilinear form is a symmetrization of a certain form which takes into account the direction of arrows. Now we know that this is 0, and that means that these two elements will have to be negatives of each other. So let me end by showing that the way I characterize whether a representation is pre-projective or pre-injective is by saying that its bilinear form evaluated on this special vector D is positive or negative. That is going to be the criterion. And the criterion is again, the criterion takes some work, but the type of work that you do is again in the root system, where you still take the still take this Coxeter element C, and you still take the same power h of it that you took in the corresponding Dynkin diagram, the one that is obtained by deleting a particular vertex, and you do some linear algebra with it, which we do not have the time to do. So I'm sorry that I cannot really complete this proof. If you want, in the tutorial, I can sort of sketch this. But this is where I would like to draw the line for this line of thinking. And so let me say some concluding things. If you have some questions or comments, then you can ask. But let me just say a couple of concluding things, which is which is what I think you should be able to take out of this as a minimum thing. So the absolutely key thing is, of course, the language of Quivers and representations, yes, indecomposables. But the key construct is reflection functors. So what you should be able to do, and I suggest that you try to maybe give a lecture to yourself, or if you can find somebody else. The summary result that we had about, so first the definition of reflection functor, then the summary that we had for reflection functors, where we said that seven properties about a reflection functor applied on some indecomposable module were equivalent. You should be able to justify all of that. Once you justify that, then the proof that for a quiver of type ADE, the number of indecomposables is finite, and in fact, you can construct all of them corresponding to any positive root is really not much. So you should be able to do all of this development on your own. Okay. So sort of an aside on the root systems, doing this will require you to handle the combinatorics of root systems. So the idea is that there is a problem in algebra which we solved by reducing it to the combinatorics of root systems. So knowing the root systems and how to handle them, at least root systems of type AN and D4. This much you should be able to. Okay. As far as the proof of the proof that we did, that the only quivers, when we characterize quivers of type, quivers whose form is positive definite or positive semi-definite, that proof, okay, that is some combinatorics, and that is also a very nice proof. But you can black box it if you want. But what I said earlier, what I said just now, this is something that you should be able to take out of this code. That's kind of the minimum message that I would suggest that you consolidate on your own, so that it will become part of your arsenal. One other thing about sort of comparing this with how the root systems came about in your algebra course. So notice some things over there. You took a Cartan subalgebra or whatever maximal total subalgebra, and you found some special vectors in the dual space of that, and you called them roots. So all roots came at once, and then out of that you chose some special ones called simple roots. There is no anointed choice of simple roots. You have to make some choice. No, you have to choose a while chamber or something, right? You have to make some choice. However, contrast the situation over here. Here, the simple roots were handed to us. In fact, we got simple roots first. Those were the basis vectors for my Zn, and I generated all other roots out of them. So it came in a different way, an interesting way. So this is just a point of comparison. All right. So if there are any questions or comments, anything, now is the time to.
I think you have got disconnected from your laptop.
Oh, sorry. Let me just. Oh, sorry. Yeah, just give me a moment, please. Sorry about this. I'm in a, I'm at home today, so the internet is slightly misleading. Let me just join it. Yeah, so take a minute to sort of look over things, and if you have any questions, because now we are going to change, sort of take a hard turn, and I will try to give a sketch of the algebraic geometry proof of this direction. Again, black boxing some facts about.
Yeah, may I ask a question? So
Yes, please go ahead.
yeah, so for that affine type diagram, so is it the conclusion that for any I and R non-negative, this C to the power minus IPI non-zero for any I and R?
Yes, absolutely.
Okay.
You are going to get
thanks.
a yes.
So two parameter family of infinite.
2n.
Oh no,
2n
no, no.
parameter,
Right. Okay, thanks.
Yeah, so yeah, I should be able to.
Yeah, but I wonder why don't you? Why can't you do the direct proof of why this C to the power minus IPI non-zero, as we did for that PI to SI? For example, instead of taking that simple reflections, we can just keep applying C plus, and the last point when we will get non-zero will be, will be PI. Isn't that correct?
Okay. So say that again. So I think Amit, I may need your help on this.
Can you repeat the question, please?
Sure.
Direct proof of this result.
Yeah, that is what.
Yeah, so he's suggesting a proof that why can't we just directly show that? So the idea was to try to directly show this. No, we just needed to show that this is non-zero.
Yeah.
Right?
So yeah.
So he's saying, I think you just start with PI, which is already
Right.
over here, which we already have over here. Now you just start walking in the backward direction, and you assume that at some point I die.
Yeah.
Then you apply C minus.
Yes. And so if I, so what do I know? Yes. So you see, but if C minus kills something, then it's an injective. So what you're saying is that if I apply this C minuses to a projective, why can't I get an injective? That's what the question comes down to, you see?
I see. Yeah.
Right. And
I think
I
one
don't know of a
one
sim-
answer
I
that
don't know
you
of a
tried.
simple way of doing that without getting some kind of criterion, some numerical criterion about what stays invariant. And that is what is going to be this quantity over here. You take one of these, and one of them will always be positive in one case and negative in the other case.
Yep, that's true.
But maybe Amit, you will have some other way of saying this, or
No, I think the one that we discussed yesterday was probably after applying C minus repeatedly, the sequence of dimension vectors that diverges. And if it diverges, then it can't be zero eventually.
correct. Okay, but okay, all right. Okay, all right. So okay, so all right. So okay, so let me just try to say this once again. In that, so what you're saying is that don't look over here, just look over here, right? These are dimension vectors.
Yeah.
So just see the effect of what C minus does to this dimension vector. So if I can calculate this and just show that that they're all, I mean, I don't even have to show. It will show that it diverges, but if all of them are non-zero, that's all I have. Or rather, if all of they will always be non-zero, that's dumb because these are positive vectors. The point is they all stay positive. I will never get a negative entry if I keep going backwards. If I do that, then that's okay, no? Because the same magic works. That means that the
Yeah, it's
reflection
kind of
functors are never, yeah.
it's
However,
kind of your sorry, go ahead, please.
So so this means that if I have to just go backwards from here by applying C minuses, and I have to have a way of calculating those dimension vectors and show that the dimension vector always stays positive. That will again mean some kind of work in the root system, but it may be that it is doable without the proof that I, the proof that I kind of hinted how to do them. I don't really know.
Yeah, it's
Okay, I
kind
think
of
we
your
can take this as an exercise, no? Because
Sure,
this is a
sure.
doable thing.
For a particular choice of for a particular choice of quiver. I mean,
Yes,
maybe
but
you take AN and then you
exactly.
choose a cycle and then
Yes.
compute this, and if you can show it diverges, then yeah.
Okay, so the right. So I guess so just taking this forward, what you're implying is that if you do an abstract proof, then you will to be able to give a uniform proof. If you want to do this calculation case by case, then you can take, okay, what happens for type D, what happens for type E, and then you will be able to do a calculation. But I don't know if there is a way of doing it abstractly for an arbitrary Euclidean quiver without
But
doing
Euclidean quiver is not a uniform thing anyway. Yeah, there are A tilde, D tilde, and E tilde. So for each one of them, you have to do this explicitly, and then you are done.
That is true, but if we see, there are some things that we know. For example, the radical is exactly one dimensional, and then there is a special vector D, and it behaves in certain ways. So if I prove some properties, then I can just use the fact that the quadratic form is positive semi-definite and Q is 0 exactly for one vector. The properties that I proved, and one more property that I did not state, that exactly what are the roots here. So I will just state this, that the roots for a Euclidean diagram are, they are not infinite, because you see, I get to add any multiple of D, positive or negative. That's one of the things that I saw, and it stays a root. But the next thing is that no, but it's still not too bad. If I go modulo D, if I kill D, then it is still finite.
Mm-hmm.
So there is still some finiteness. And so you see, if I take the same C, small c, that is the sigmas chained together, then on this set, it is still going to be work as before, right? So I can now still say. So earlier, what did I say yesterday? Yesterday we said that look, no vector can be an eigenvector for C. No vector can be a fixed vector for C. We showed that yesterday.
Mm-hmm.
No non-zero vector. Well, now what we will say is that, yeah, but the only way that something can be an eigenvector for C is that if it is going to be coming from this special D, a fixed vector under C. So there is extra analysis to do of this of a similar type, but you have to do some more work. So let me just see if I can. Excuse me.
Yes.
So this is. If it doesn't work in a few seconds, then I will just.
No, I think you can just continue talking. Yeah, you just have 20 minutes left, so just continue with the
Right.
iPad. Yeah.
Yeah. Okay. All right. So let me go on to. So now we just do something completely different. Okay. So I have this notion of a variety of representations. So what I do is the following. Okay. What is a representation of a quiver? It is just some vector spaces at each vertex and some matrices, right? So now what I do is I take a variety of representations with a fixed dimension vector D, right? And so that means that what I do is that so I just put at every vertex a fixed dimensional vector space. So if I have this if this dimension vector d1 up to dn, then I have just something of dimension di and dj in whenever when so and now what and now what does it mean to give some what does it mean to give maps? So whenever there is an arrow from I to j, I have to put a matrix over here, right? Well, what matrix will that be? It will be a matrix of well, I guess strictly speaking, d sub j times cross d sub I, right? Never mind. So I just put such matrix. So if I just want to take collectively all such representations, then I can identify the vector space that I put at vertex I with k to the di actual column vectors. And then I say that all representations are really just given by this space, which I call E sub d. I just put as many matrices as the number of arrows. Yeah, that's what a representation is. Okay. But to say that there are these many distinct representations is ridiculous, right? Because I want to take into account isomorphisms of representation. So let us consider when two representations are isomorphic, right? And that is going to be precisely a change of basis situation. All right. So let us say, what does it mean to have a morphism between two representations? It should work now. Yeah. Okay. So I hope that is working now, the video. Anyway, so what does it mean to have a morphism between two representations? Well, it simply means that whenever there is an edge I to j, I have these maps in the two respective representations m and m prime. And now I have these invertible maps for isomorphism. For morphism, I have just these maps gi and gj such that the diagram commutes, correct? But what I want to see is the picture that I have taken over here. I want to go modulo the isomorphisms. I want to regard two different representations given by two different sets of matrices. When are they the same? Correct. So that just means that there is an isomorphism. So think of this mi again as k to the di and this also as k to the di. And what it means is that I have a commutative diagram over here for every edge in the quiver cube. But what does commutative diagram mean? It means that going this way is the same thing as going this way. But that simply means that going this way is the same thing as going this way. That precisely means phi prime alpha is really the same thing as first GI inverse, then phi alpha, and then GJ. So what this is saying is that, look, if I want to find out, if I want to count representations up to isomorphism, So the word indecomposable has not come here at all. Okay, I'm really starting ab initio. I'm just saying all representations finite dimensional, and I'm just want to count how many are different up to isomorphism. Then this is the answer. Take this E sub D and let the group GL. Sorry, this is K to the DI. Okay, so GL K to the I had written the. This is the same thing I had written. So this is DI cross DI invertible matrices. And having an isomorphism between two such apparently different representations simply means giving a family of invertible matrices to this phi such that uh, the phi's between the respective representations are related by this formula. But now I'm just going to identify all the mi, mj, and these simply with k to the di and k to the dj. So this boils down to saying that I should take all such matrices, but I should consolidate a family whenever I have a set of matrices on which this action is there. So this, so I can now simply write, I can simply try to write this as this is G dot phi P dot phi. So this is to be understood appropriately. This one is the collection of all of these arrows, and this G is the collection of all of this is the compatible family of all these GIs, one at each vertex. Okay. So the upshot is that the isomorphism class of a given M, or you can just think of this as M is of M with dimension vector P, is really I just put these K to the DIs everywhere. I take all such families of matrices and I take the quotient of this. That is, I let the product of these GL DIs act on it and just see how many orbits there. Because everything in the orbit is going to be equivalent to each other. And of course, given an orbit, there is a representation like that. Namely, just pick one such family, right? So this is the translation. It's a very simple, I mean, it's a standard way of thinking. But if you have not seen this, then if this is the first time, then it may take a little while to see what is going on. Just give me a moment, please. Just give me a moment, please. Okay, so yeah, so that means what that means is that if I want to count the number of representations up to isomorphism, then I have to count the number of these orbits, right? So there are some facts that we want to say, that these are all algebraic varieties, and there is a notion of dimension, and we can count dimensions. So for the space E sub D, this is very easy. This is just a bunch of matrices like direct sum. So what is going to be the total dimension? The dimension of this is just di times dj, and I'm going to add this over all arrows, right? So that's just an affine space. This is what I have. The group G also has a dimension because it's an open set in the space of square matrices all chained together. The open set will have the same dimension as the ambient space. So the dimension of GL of GLN is just n square. And I'm taking the product of these, so the dimensions add, so that this dimension is going to be summation di square. Already you see the quadratic form is taking shape in front of our eyes. This summation di square minus this one is going to be my quadratic form, right? Associated to the vector D. Okay. Very good. Now, you remember our standard formula in the first group theory course, the orbit stabilizer. What does it say? That if I have a finite group acting on a finite set, then what does the orbit is what? Is G modulo the stabilizer, right? So the size of the orbit is really the number of cosets of, so it's the size of G mod the stabilizer. The analog of that formula in this situation is that the dimension of the orbit of M. So I have taken a particular representation. Remember that this particular representation in my affine space is just a point. All right. The point which is indexed by all the matrices of all the maps that appear in M. So if I take the dimension of this orbit, then it is also G mod stabilizer. The analog of that is that it's the dimension of G minus the dimension of the stabilizer. Now the stabilizer of M, it's really just the space of all endomorphisms of. Okay. The reason for that is that the stabilizer of M is a group. So it is going to have the same dimension as the ambient space in which the affine space in which it's sitting in. So it is going to be really the same thing as a vector space dimension of the space of endomorphisms of M as a representation. Okay. So we are almost there. One more thing to say is that because the algebraic geometry tells us that there is at most one dense orbit. That is an orbit that has the same dimension as the entire ambient space. Okay, so we are just going to take these facts as black boxes. All right. So what do we want to show? We want to show that the number of
could you please explain what is the dense orbit?
Yeah,
what
so
is
dense
a
orbit,
dense orbit? I mean, just the definition.
Yeah, so dense means that its closure is everything.
Okay. Generic point isn't like, okay.
Okay, yes. All right. So remember what our goal is. The reason why we are doing all of this counting is we want to count the number of orbits. And the kind of counting that we are interested in question is very crude. We just want to say whether the number of orbits is finite or not. Okay. So we will show that if the quadratic form is not positive definite, then the number of orbits is infinite. That's all that we want to show. Okay. All right. And like before, we will just reduce to the Euclidean case. All right. So let's take a connected quiver Q, and so I have some arbitrary M representation F of M of dimension D. So let's try to count what the co-dimension of this orbit is. Right? How big this orbit is. Basically, what we are trying to show is that the co-dimension is at least 1. So this is not a dense orbit. Okay. And you see, what that tells you is that if I want to, let me complete the proof before seeing the details. So if I show that the co-dimension is at least 1, what that tells me is that the dimension of the ambient space, you should think of this, the intuition is really in terms of subspaces. So if you have a if you have this ambient space, and if you have these orbits that are sitting inside, and if the dimension of each orbit is strictly less than the dimension of the ambient space, then the ambient space cannot be filled with a finite number of these orbits. This is like saying that if I have a vector space, then it is not a union, not a finite union of proper subspaces, provided your field is infinite. Okay. So in this situation, I am really assuming that, let us say I'm working over an algebraically closed field, so my algebraic geometry works nice. All right, so let us try to do the dimension count. So what does it say? Co-dimension is just the dimension of the ambient space minus the dimension of the orbit. That's just the definition of co-dimension. Okay, so let's write down what is the dimension of this representation space ED. We saw that it really is just take all the matrices, right? So the matrix space is of size di dj for every vertex, for every edge from I to j. Now let's plug in what the dimension of the orbit is. Okay, so this minus sign goes for a goes along, and the dimension is the dimension of the group, which is the summation di square, and I have to subtract from that the dimension of the stabilizer, which is the dimension of the endomorphism space of M. So that becomes a plus. All right, so let's take a look. That's really the same thing as the space of endomorphisms of M. Remember, endomorphisms of M is at least one dimensional. Why? Because there is the identity map, so all the scalars are there. So this is at least one dimensional. And what did I get over here? This thing over here is just minus of the quadratic form evaluated on the dimension vector D. So what we saw is that this co-dimension of the orbit is the dimension of the endomorphisms minus this quadratic form. So what happens if there is a if there is a dimension vector D, any dimension vector whatsoever, whose quadratic form is less than or equal to 0. So I will always get this in any non-Dinkin case, correct? Or if you want to reduce to the Euclidean case, then I in fact found something like that in the Euclidean case, no, namely the special vector D. That is the one that I take to be this D. Then what happens to the codimension? The codimension is, see, this is this. So if I get something where this is 0, then the codimension is the dimension of the endomorphisms, which is at least M, which is at least 1. So the dimension of the ambient space is strictly bigger than the dimension of any orbit for this particular dimension vector D. And that means that the number of orbits for this dimension vector D is infinite. That means the number of isomorphism classes of representations, period. I'm not saying anything indecomposable, etc. We will come to that just in a bit. So just the total number of isomorphism classes of representations with this dimension vector is infinite. Now it's just a small matter of seeing that this means that I get infinitely many indecomposable representations themselves. Why? Well, let's suppose that there were only finitely many indecomposables, right? If the finitely many indecomposables, let us say, were like sum of dimension 1, sum of dimension 2, sum of dimension 3, and so on and so on, right? But I have to stop at some place. So if these were all the indecomposables, then every non-indecomposable finite dimensional is just, its dimension is just obtained by adding these numbers with some, in some way. So you see, if I want to get a representation of total dimension 100. So by the way, so by dimension, I just mean the dimension of the total, that is the sum of the DIs. So if my indecomposables had these total dimensions, let's say, only finitely many, then how many representations of dimension 100 can I have? Only finitely many, you see, because the only way to build an 100-dimensional representation is to take some of these ones, some of these ones, some of these twos, and so on. So the number of ways to write 100 as a sum of this multiset is only finite. I do not even need the Krull-Schmidt theorem here. I do not need uniqueness, because if some of these ways coalesce together, if there is a way to write a same 100-dimensional representation in two different ways, that will only reduce the number. So this is just for a very simple reason. As long as the total number of if the total number of indecomposables is finite, then for any dimension, any finite dimension vector, I will get only a finite number of representations, period. So conversely, if I have obtained a dimension vector for which there are infinitely many isomorphism classes of representations, there have to be infinitely many indecomposables as well. Done. And I'm also done with the time. So
Any quick questions?
I think I will just stop here.
Any questions? Okay, so in that case, so from the organizers, let us I would like to thank Professor Kulkarni for delivering this wonderful lecture series. Many thanks. So
Well, I don't
this
know about
was
wonderful. I tried to do something, and what I said, I really don't know anything more than I said. This is like the sum total of
no,
my knowledge. So I'm
I'm
sort of looking
sure
forward
it
to the.
reached.
I'm looking forward to the remaining things. I hope it was okay for you guys. You learned something. And
I'm
thanks
sure
very much for
participants did learn
allowing me
something.
to sort of explore my ignorance and try to reduce it a little bit. So